All right, all right. Let's get started. So, um, let's see. Last we met, we were sort of redoing the load cases on this guy while going over uh, sort of the slide deck, explaining what in the world this is. So I put a little more work into the slide deck, updated the pictures, learned a little bit more about uh, topology optimization in general. So let's go through the slide deck real quick, and then we'll figure out where to go from there. So topology optimization, it's a mathematical method to optimize material layout within a given design space. So that you also have to add a set of loads, boundary conditions, constraints, and it will optimize for the maximum performance of the system, whatever that means. That could be mass, it could be temperature, some fluidics properties, you name it. So I'm not going to go into the differences between topology optimization and generative design or shape optimization right now. It's a young technology, and people are still disagreeing about what these terms mean. So there's really no winning in that case. So let's address another common question. Why not just run normal structural FEA, thermal analysis or whatever, and remove low stress areas? It's like why not? All right, so we're gonna jump into this. Quick disclaimer: this example is for entertainment purposes only, and ignores almost all best practices for design, simulation, and manufacturing. That being said, let's jump right in. So here's your original bracket. It weighs 135 grams. We have a 100 Newton load applied here. We have a max deflection of 5.6 times 10 to the negative third millimeters. Pretty small. So we're going to target 70% reduction in mass. And a less than 0.1 millimeter deflection. So about 4th out. Basically nothing. So here's our stress-based material removal. See here, we've just removed everything on the iso clipping line. Push any more than this and you start getting completely disconnected here. So we didn't do that. So I modeled it parametrically. And here we go. It has a mass of 92 grams, nowhere near our targeted reduction. Let's add that in for reference. 40.5. So yeah, nowhere near targeted deflection, or yeah. So we got 2.7 times e to the negative 2. You know what? I'm 1 e to the negative 1. Yeah, that's better. Negative 1, not 0.1. Goodness. So it does hit the deflection requirements though. So maybe this is okay. Let's see how much better we can do. Here's topology optimization. So this starts to look a little bit more intelligently designed here. We've got a like a truss structure, which you might recognize. Some better handling of the load. So like you can imagine the load path coming down, and then you got your truss structures here. Makes a lot of sense. So the mass is 41 grams. So we hit our target, and the deflection is also even less than the stress-based material removal method. So there's a lot of math behind this, but I think this is a pretty intuitive example of why a low stress area can actually be contributing to the stiffness of a structure. It might not show up on your von Mises stress charts, but it is actually doing something. So an understanding of load pathing is critical. However, sometimes you've got a lot of loads, complex loads, complex geometry. Maybe the load pathing isn't super intuitive, and you're shooting for something pretty optimized, and you just don't want to guess and check 100 times trying to come up with something. So that's where topology optimization comes in. So the example we're going to use is quadcopters. Weight and stiffness are critical for flight characteristics. And to achieve sort of the maximum advantage from topology optimization, we're going to use 3D printing to just accommodate the ridiculous geometry this is going to generate. It's like you're not going to want to machine this, or pretty much any other traditional manufacturing method is going to be pretty terrible. So requirements we're going to try to hit is total system weight. Must be under 250 grams. Frame size should be under 3 inches. Thrust to weight ratio at least 4 to 1. Otherwise, you're just going to barely be hovering, and then it should be around 10 to 1 for some more acrobatic characteristics. So load cases. Jump right into how we set this up. The main forces the frame experiences are due to the motors, both the thrust and the reaction force. So we're going to estimate that from our data sheets. We can pull from some manufacturers. This particular one comes from T-Motor. So we're going to estimate 15.7 newtons of thrust at 16.97 newton meters of torque. Seems about right ballpark wise. Now, here's a neat thing for topology optimization studies, sort of in general. So imagine you have like a beam and bending, say your typical cantilever beam. If you have a load down, right, and you simulate it, this is going to give you one thing. If you have a load up, it's going to give you basically the mirror image. But if you apply both loads at the same time and then run the scenario, they will cancel each other out, and you will get a simulation that's sort of resisting compression more than any bending in both directions. Now, with the structural analysis, you can do this with multiple passes. Fairly intuitively, you can have just a different simulation for each load case, and you can go through and manually check that everything lines up. So this is more of a convenience feature in that case. But for topology optimization, you really need to know all of these cases at the same time. So the load case manager lets you define scenarios, which are combinations of multiple loads. So each one of these is a load in the SolidWorks sense. You can turn them on and off and change the values. And they all apply at the same time, and then uses a 40-40 split. I think there's some weird matrix math going on in the background to get an optimal solution for each. Sort of like balances the performance in each load case. So here's space claim. This is a somewhat iterative process. So ideally, what you would do is you would have a space claim that handles your entire design space, like everything everything possible size-wise that you could let the algorithm play with. So what happens is you then set a target for reduction, and the algorithm tries to hit it. Now, the tricky bit is it doesn't really like it if you're removing more than 90% of your original mass. It really bogs down. So you're better off having as small of a space claim as possible, and uh, going from there. Now, it can be beneficial to run a couple coarse estimations to see where you might need to add material or remove material. But one of the drawbacks of topology optimization is that it is mesh dependent. So you will get a different result per mesh type that you use. Now that I'm talking through this is probably worth a short slide. That's interesting. These are all research papers. This is going to be tricky. I really should have saved that paper. Well, here we go. We're just gonna do it in Paint. Okay, so imagine you've got a box here, or a beam. It's a terrible beam. You've got a load here, and you have to remove 50% of the weight. You've got a very coarse mesh. So what you're gonna do is you're gonna make just one hole that cuts away 50%, right? This is okay, but the deflection is also okay. But let's think about this a little more. What if instead of one big hole, you put 4 small holes? Same load, same mass, remove the same amount of mass, but now your deflection is significantly less. And why stop there? You can just keep doing smaller and smaller holes, you know, ad infinitum, and eventually you will turn this into foam. This will just become open or closed cell foam, and that will be the optimal structure based on your mesh size. So that's sort of a crude example of what mesh dependency means in terms of topology optimization. This is a problem with the math, and different software uses different approaches to make sure your design just doesn't turn into foam every time you run the study. I have no idea what SolidWorks uses behind the scenes, but what this means for us is even with all their clever tricks, the coarseness of the mesh you use will influence the actual results you get. Not just the resolution of the results, but the actual result will be different based on your meshing. Let me just toss this in here. Features become more intricate as the mesh gets refined. The mesh. Oh, how did I word that earlier? The resolution, the mesh. This is kind of a wacky topic. Um, See, these are all like research papers, which is cool for like trying to understand uh like what's actually happening behind the scenes, but like at some point you need to actually know how to use the software. Um, and this is a 200-page paper on something. Um, I know I found an explanation that was quite good. Yeah, see, this is like a pretty simplistic definition. It's just like make it finer. Uh, for finer, here it is. This is what I wanted. Um, do do do. Just not gonna lose that again. Bum bum bum. This is useless. Yeah. See here you go. Here's that example I'm talking about. You just increase the number of holes until it basically becomes a foam, and you can see here your compliance decreases as your number of holes increases. It's pretty rough. So this paper is not at all helpful with how to actually pick a mesh fineness, but it does give you some insight into what's going on behind the scenes, which is also useful, at least indirectly. Are we gonna what does ANSYS have to say about this? create a mesh. Yeah, that's fine. So the rule of thumb that I'm finding is the maximum mesh element. Let's see, maximum, minimum. I will get there. Minimum feature size must be at least 4x the mesh element size. So you need to be able to fit um, four mesh elements through your thickness. This seems to be the case. Following that sort of guideline seems to give maximum member size must be at least 4.4x mesh density. Maybe that's what's giving me a headache. So I've been having issues with this, right? Because like as you increase the density of your mesh, you drastically increase the time it takes to execute your study. A coarse mesh could execute in 3 to 5 minutes. A fine mesh will execute in closer to 3 to 5 days, which is rough because I use this computer for other things. And having it tied up with at least one core completely maxed is not super great for me. How am I going? Member size constraint larger than the original thickness. You know what? This is a 50-page study. Seems to be fairly comprehensive. I'm just gonna go through this on stream. I hope you all like PDFs. Here we go. Page fit. Zoom. So this seems to be from a consulting company. Hopefully I can glean some wisdom. Um, so this is just how to do ANSYS. Which is in general much nicer than SOLIDWORKS, but such is life. All right, 50%. Oh, that's wow. These are great features. Man, I wish I had this. I wish it didn't cost basically my salary to buy this. You can watch it in real time. I'm just making myself sad looking at this. This is pretty crazy. Okay, simply supported beam, point force, symmetry constraints. Uh, oh, interesting. Okay, so they put symmetry and then added. Okay, that's neat. Um, I hadn't considered using the um, pull out direction to get that type of approach. I wonder. 5 load step model mass minimization. I don't think that really helps. Helps me anyway. Okay, so here they got the exact same results with a coarser mesh. Um, got some more manufacturable results, which we don't really care about. Um, okay. I don't think SolidWorks lets you make hollow ones. All right, well, all in all, I think if we follow the recommendations per the ANSYS thing, um, it's probably pretty safe. Um, uh, if if ANSYS has a limitation on this technology, the odds of SolidWorks overcoming that are slim to none, in my opinion. So let's go over these um, preserved regions. So what we've done here is we've um, added these as a. Oh, maybe that. Oh, is that why? Is that why this isn't working? Okay. Um. Anyway, to complete my thought, I set these as preserved regions, but did not give them a preserved region depth. I then came in and gave a minimum member thickness of 3 millimeters. Um, now, I didn't go in and like actually check the geometry um, to see if uh, there were um, any issues with the actual model. Geez, I'm being dense here. I know there's a thickness analysis. Of course, right there. Calculate. Hey, okay, so there are in fact areas here that are smaller than 3 millimeters. This may in fact be um, causing me issues. Um, that is silly. Fortunately, it's somewhat easy to fix. So we're gonna come in and we're gonna roll back to here and we're gonna create some geometry, which is stupid. Um, so we're gonna force it. Yeah, there, boom. Right? Yes? No. Yeah? Okay, there. Yeah? And we're gonna go here. Same thing. We're gonna probably make it like 4 though. So anyway, I was dying trying to figure out why this kept failing. It would be really, really silly if this was the issue. Are there any reasons? Resolution. Maximum. Um, okay. I don't really like these sharp corners though, so I'm just gonna smooth those out. I know it's silly, but um, well, what? Maybe not that intense. Maybe a little less intense. Fine. Did I accidentally remove material? Let's double check. I did. I did, in fact. So we're going to do it again. Made the same mistake. Interesting. Okay, can I? Intersection. Okay, that works. And then we're gonna construction, make it collinear. This is probably the dumbest way to do it, but here we are. Calculate. And it's still low. But why? Solution is clearly to just extrude more faces. Um, clearly. Clearly this is optimal. Is this? Fine, whatever. Extrude. Flip. Or yes. All my fillets are clearly broken. I, in my hubris, added fillets before the last step. Yeah, alright. I don't hate it. Thickness, one last time. Max res. Wow, that was dumb. So, let's try this again. I need to go grab a scale and or a measuring tape. I need to see how big this thing is. Okay, we have returned. So you know what? Let's look at what our actual mesh parameters here are. So it's saying 1.5 is our default size, and I know this solves relatively quickly. Now, if I do that times 4.4, that's a 6 millimeter minimum wall thickness. And that's not crazy. So let's, oh, I did not. Let's go here. How much work do we have to do? See, that's a pretty fine mesh. So let's go in here and look at the thickness and check for anything under 7. So there's probably some spots here. Like I can't imagine. Yeah, the whole thing. Wow, okay. So we're gonna get rid of the lightweighting, suppress. Why isn't my real 3D showing up? instant 3D, sorry. 8. 8. Whatever. Fillets. 8. Everything's broken. Now, maybe it won't have a stroke now. Oh, it's close. So this is now 4.4, and I need it to be at least 7. So I just need to make it a little bit bigger. Does that fix that area? Oh. That fixes that area. That changes nothing. So now we've got this, and this, and this. So that's clearance. How did I do this? There's a, yeah, so this guy just needs to get 3 millimeters bigger. No, stop that. 2 millimeters. Let's go 17. Yeah. And this guy, we'll just take that to 7. Neat. All right. How about now? Oh, I missed a spot. But just confirming. Oh, right. Yeah, and then of course this is going to have issues. You know what? Maybe this will work. No, it most definitely will not. Let's convert this. Yeah, yeah. How about this? Still, it's looking pretty dumb right now. Yeah. Okay. Like this. What isn't it liking? How am I messing this up? Because that's 7. Oh, oh, what's going on in here? We're gonna do this. Um, yeah. Flip. Basically just blowing away all that internal geometry. Hopefully that'll get rid of a little weirdness in there. Um, let's make a note of what we're doing here. Um, and there. Oh, what? Oh, okay. I mean, am I ever going to be able to get rid of that? No, not really. No. Um, Now the other one is just straight up. So that's 6. So that needs to just go to like 7. And is there any way I can actually? Am I missing some sort of like internal geometry here? No, it's just that it's a corner, I think. Now the question is simulation going to care about that? Because like maybe it doesn't, maybe this is fine. Where are we at? Um, I just don't think there's a way to fix that exactly because um, like I can't, like I need this surface. Yeah. So let's see if it runs. So we're gonna change our minimum member thickness to uh 7, I guess. And then we're gonna look at our mesh again, rerun that guy. Now, if we run this study, at the very least it should fail quickly. Um, we have at least earned that much. Um, where's the execution dialog box? It is still thinking about it. There we go. All right. So now if it fails, it should fail before 1%, and it should say something like study has failed, and not give any reasons, because this is SOLIDWORKS, and we can't have nice things. Um, it's actually going. Now we did just add a bunch of mass to this, so the odds of it hitting, well, I mean, obviously we're going to miss our mass target. But that might actually be fine, because there is 0% chance I'm going to actually make this 7 millimeters thick. So we'll reclaim some mass from that. So let's go back here. And did I just change this whole workflow again? Let's continue on, assuming that these two slides don't exist. And we'll just have this fella up. I got him off to the side. He's at 5% already. So should be under 20 minutes. Get that guy working again. Right. So fixtures. So you got to hold this thing in space to actually apply the loads, do things to it. So fully define it. We've made a fixed surface here, and oh, so our fixed surface is here, flight controller stack. That should be the most accurate method I could figure out to fully constrain this guy. It's not like it's sliding on any particular plane, and the motors sure aren't fixed. So this is my best guess. Then we've added a symmetry plane here because it is in fact symmetric on that plane, and that really increases our simulation times, like more than 50% reduction, which is great. And some of the sharper-eyed among you may have noticed that this is a thing flying through the air. So hey, why not use inertia relief and just have the inertia of the thingy handle the fixturing for you. That would be a great idea, except the math just doesn't work out. According to the simulation guy I talked to, the matrix math just doesn't work out for topology optimization. So scratch that. So these are the loads. The magnitude isn't particularly critical, but the ratios are important. So we've got a maximum thrust case where all four motors are firing at once. And to talk about the yaw, we're going to go a little bit into quadcopter flight dynamics. So up and down is pretty intuitive. You just fire up propellers and you shoot into the sky. But getting it to roll and pitch is just slightly more complicated. So if you look at the diagrams that I've got up here, to roll to the left, what you would do is you would spin up props 1 and 2 and decrease on 3 and 4. So you're going to rotate to the left. And similarly, for pitching back, you'd spin up 2 and 4, decrease 1 and 3, and pitch back. Now, yaw is a little less intuitive. So you'll notice that we have 2 sets of propellers here spinning in opposite directions. So what that does is for level flight, you're going to spin them up the same amount in each direction, and so the counter rotation cancels out, and you stay pointed forwards. But if you were to speed up one side, conservation of angular momentum says that it's going to spin. The whole system is going to spin the other way. So that's how quadcopters turn. So what we've done is we've kept the overall thrust load the same, which is an estimation, right? And we've gotten rid of the opposing motor in one case. So we've assumed one motor is spun completely up and the other is completely down, and then we've reversed that for the other load case. So moving on, our optimization goals here are primarily a mass constraint. There's some really neat ones for like displacement constraint and even a frequency-based constraint. Stress and factor of safety is, I would not trust that. I would suggest running off of mass constraint, doing your design and then testing it. I just don't really trust it. You ballpark number out of it probably, but I wouldn't I wouldn't um, I wouldn't trust it. So undershoot the mass target. So when you convert from these nice, smooth, curvy, or maybe chunky kinds of models here to something that you can actually like do surface modeling or sweeps or just extrusions, it generally adds a little bit of weight because you can't follow those curves exactly. So we're going to target something a little less than half of our 30 grams that we're shooting for. So our manufacturing constraints are, so these regions we got to keep. Reserved regions, mesh control, thickness control, 7 millimeters. So these are the regions that we need to keep to make this thing actually function as intended. And here are our simulation settings. These will get you if you're not super familiar with SOLIDWORKS simulation in general. There's this simulation setup tab. So you need to go in there and make sure this matches what you're actually doing. The critical regions here are the preserved region settings on both the options and advanced tab. You got to set those to none, otherwise SOLIDWORKS will start adding in stuff in what seems to be a semi-random fashion. Very frustrating. Ask me how I know. Then the min-max formulation here is required to be checked if you are doing multiple load cases, which we are. So just check there. Here is where I would put my final results if I had them. It just decided to finish. Is this real? This looks like garbage. What happened? Did it fail? It must have failed. This isn't real. This is suppressed. How did this get suppressed? Was that me? That was me, wasn't it? I suppressed it just now. Ah, jeez. How embarrassing. I can watch myself do it. I can go back in time and watch myself do it. Ha! Yep. That's what I did. How disappointing. And now I can't view the mesh anymore. Rest in peace. At least it was only 10 minutes. Let's go in, look at mass properties. So what we got 328. Ah, yeah, that's why. So we're gonna come in. No, that's not acceptable. So we need to remove it, reduce it by like 355. Or sorry, two. Oh, 305. My bad. Oh, no, that's still not right. We need to be getting this down to like 11. Watch me struggle with basic math. 315. Okay, that's going to yield a very different result. Let's look at this mesh again before we go here. Ah, no, this has got to be. Oh, now that qualifies as fine. Okay. Oh, whatever. Why is that a fine mesh now? Whatever. That's why you do manual control and you don't use that stupid slider. Um, Back to the slide deck. Here's where I would put that mass if I had it, but I don't. So there it stays. Let's see if I can't make more sense of this mesh dependency. Can I get shamelessly stealing pictures? That's shorter and punchier. Um, it's How are we doing here? Still at 0%, 2 minutes in. That's not a great sign for me. Okay, mesh density determines design. Increasing density drives more intricate features. What's this? Uh, Oh, I'll get that in a second. All right, meshing. Minimum feature size was to be like 4x the mesh. Minimum feature size, mesh element size. Well, I mean, we don't know that. The feature the hasn't actually run. Uh, Even this is going to take longer. Anyway, I'm losing steam. I got some stuff to do, so I'm gonna head out. Hopefully this analysis goes well and get back to more actually modeling it and getting this thing printed before my license expires in 27 days. Anywho, I will catch y'all next week. Have a good night.